Ben bir mühendisim. Ofiste, evde, yaşamın her alanındayım. Görülmeyen ama hissedilenim. Ben ne kadar görünmez olursam, projelerim o kadar başarıyla tasarlanmış ve uygulanmış demektir. Tıpkı sizi sizden fazla düşünen gizli bir kahraman gibi. Kahramanlık, kağıtla kalem bir araya geldiğinde geleceğe yön verebilecek kadar cesur olmaktır. Çünkü mühendislik, bilim ve doğa alanında tüm bilinenleri yine doğa ve insanlık için kullanmaktır. Tasarımda sadece estetiğin değil, sürdürülebilirlik, enerji verimliliği, çevre duyarlılığı gibi kavramların da altını çizmektir. Mühendislik, modern, konforlu ve doğaya saygı gösteren yenilikçi yaşam alanlarını hayal etmek ve gerçeğe dönüştürmektir. Gelecek kuşaklara yön vermektir. Binlerce yıl önce bir kıvılcımla yaratılan aydınlığı bugün tek bir tuşla milyonlarca insanın yaşadığı yerlere taşımaktır. Geceyi gündüze, soğuğu sıcağa, sıcağı soğuğa çevirebilmektir. İnsanlığın ihtiyaçlarını karşılamak için hayallerimizi gerçekleştirirken yanımızda TTMD vardı. 1992 yılında kurulduğundan bu yana çatısı altında güven bulduğumuz, etik değerlerin teşkili ve temel sorunların çözümü için birlikte çalıştığımız yol arkadaşımız. Farklı disiplinlerden gelen profesyonellerin ortak amaçlar için toplandığı TTMD, üyeler arasında iletişim ve tartışma ortamı yaratıyor, bilimsel ve teknolojik yayınlar yapıyor, üniversite, sanayi, işbirliğine destek veriyor, çevreci ve enerji verimli çözümlerin yaygınlaşmasını destekliyor, yurt dışındaki gelişmeleri izliyor ve sektörü yurt dışında temsil ediyor. Bizler tüm insanlığın iyi yaşam arayışına çözüm buluyoruz. Bizler yarınlarımızı şimdiden kuruyor ve daha sürdürülebilir bir dünya için çalışıyoruz. TTMD, 1992'den bugüne yaşam mekanlarında insanlığın konfor ihtiyaçlarını doğaya saygı göstererek sağlamak için var. Mühendislik mesleğini etik değerler doğrultusunda uygulamak için var. Türk Tesisat Mühendisleri Derneği. Gelin geleceği birlikte yaratalım.
Okay. I think we are on now. Good afternoon, ladies and gentlemen. Welcome to another webinar of TTMD with collaboration with the ASHRAE Turkish Chapter. My name is Gülsu Ulukavak Harputlugil. I'm an associate professor at Çankaya University in Architecture. And today we are hosting two very important and distinguished speakers, Dr. Crowley and Leung. Before I'm going to give the screen to our speakers, President of ASHRAE Chapter, Mr. Ahmet Gökşen, would like to welcome you. But before I leave the screen, I just want to remind you that if you have a question or comments, please use the questions and answers part on the panel. And this is just for the audiences. And now, Mr. Gökşen, please.
Thank you very much, Professor Gülsu. Dear Drew, dear Luke, and dear attendees, on behalf of ASHRAE Turkish Chapter and TTMD, I would like to thank you for participating in the Decarbonization and Electrification webinar. Mr. Meriç Sapçı, the president of TTMD, sent his best regards. Unfortunately, he cannot join the meeting and sent his best wishes for the webinar. Like in every ASHRAE meeting, I would like to remind the ethical rules of the ASHRAE. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and we shall avoid all real or perceived conflicts of interests. If you like to read full version of ASHRAE Ethic Rules, you can visit ASHRAE.org website. Today, the issue of decarbonization is gaining more and more importance all over the world. I hope that the information provided by the distinguished lecturers in this webinar will shed light on us. I wish you a good meeting. Thank you.
Thank you so much, Mr. Gökçin. Well, actually, I don't want to make you too much wait. Just, our first speaker is Leung. He's going to give a presentation on the subject of decarbonization, bending the carbon curve. Before I leave the screen to Mr. Leung, I just want to introduce him to you. Luke is a lead fellow, ASHRAE fellow, ASHRAE Epidemic Task Force Commercial Team Leader, ASHRAE Task Force for Building Decarbonization EXCOM, ASHRAE Directors at Large, Carbon Leadership from MEP 2040 founding member, City of Chicago Decarbonization Task Force, ASHRAE Distinguished Lecturer. He is the wide firm principal of the Sustainability Engineering Studio for Skidmore, Owings and Merrill. His work includes Burj Khalifa, the current world's tallest building, and other 4 of the top 20 tallest buildings in the world. So the screen is yours, Mr. Leung.
Thank you. Thank you for the invitation here. Can you see my screen right now?
Yes.
Yeah. Okay. Do you see it is a normal mode or presentation mode?
Well, actually, we are now seeing your screen in normal mode, not the presenter one.
I see. How about now?
Yes, now it's presenter.
Okay. Okay. So it looks like your presentation screen, right?
Yes, exactly.
Okay, correct. Thank you. So bending the carbon curve, by the way, thank you for allowing me to join this very exciting seminar. So there are 3 things I would like to share with you. 1, why bending the carbon curve is a moving target. Number 2, how do you optimize whole life carbon? And number 3, 4 elements in whole life carbon. So diving right into topic number 1, why looking at whole life carbon is a moving target? Well, just look at Turkey as a whole, right? So this is taken at the shot about 6 a.m. on March. And at that time, you can see the carbon emission per kilowatt hour is 523 grams of carbon dioxide per kilowatt hour. It's light brown color, meaning that it is kind of, darker the color is not so good, lighter the color is better. So it's kind of in the middle. In fact, Turkey's carbon emission at that kilowatt hour is roughly about world average, maybe slightly higher than world average, which is at about 500 gram per kilowatt hour. But that's not always the same. If you look at the chart here, on the left here, what you see is 540 gram, and it happened at 10 p.m. And on the right is 448, and it happened at 4 p.m. in the afternoon, right? So you can see the time difference, and as a result, the operational carbon difference. So why is that? Because at that time, when it's 4 p.m. in the afternoon, the grid, as you can see on the right here, the blue is hydro. It has more hydro, and kind of the purplish, reddish color is gas. So it has more cleaner sources of energy. Also, wind is kind of the light green. So that's why the generation is actually cleaner, because compared to on the left here, majority of the energy is that light brown color bar, which is coal energy. So it's a moving target because it actually moves. And I'm not even talking about embodied carbon, I'm talking about operational carbon. And when you look at embodied carbon, the x-axis is different types of buildings, and the y-axis is embodied carbon. Now the range here is about 250 to about 1,000 plus, right? So there's a wide range of embodied carbon. But if you zoom into specific building types, like look at office building, though we know roughly it's about 500 kilograms CO2 equivalent per square meter, the embodied carbon usage intensity, but it varies. Like if you go to hospital and health, right, it's actually could be anywhere 600 to 1,000. So still there's a range of target that we don't really have a exact handle on the type of benchmarking we have, though we now better the range. So it's not only a moving target in operational, but also embodied carbon. Part of that reason why embodied carbon is moving is, now if you look at the range of embodied carbon, roughly about 250 to 1,100. Well, how much of that is mechanical, electrical, and plumbing, right? This is an office building. So if you remember that roughly about 500 plus or minus kilogram CO2 equivalent per square meter of embodied carbon intensity of its lifetime. The upfront carbon, which is the red bar here, that is how much carbon it takes to build a building. If you add all the red bar together, 40 plus about 10 and 10, it's pretty less than 100. That's upfront carbon. So roughly about 100 out of 500, maybe 20% of the MEP upfront carbon out of 500. That doesn't sound very significant, right? It's maybe 20%, 100 out of 500. But if you include the lifetime of MEP carbon, because as you know, air handling unit chillers, they may last about 20 years. So if you have a life cycle of 60 years, you're gonna have to replace it 2-3 times, like what you are seeing here. Once you add the gray bar, which is the replacement cycle of different elements in an office building, B4 category, okay? So all of a sudden, it becomes quite significant, because if you add all the bars here, roughly the lowest is about 80, the top is about 50, so that's 130. So this is roughly about 200 plus. So 200 out of 500, all of a sudden you are talking about MEP embodied carbon is about 40% to 50% of the embodied carbon of a building. So it's a significant component, and we have to include that MEP embodied carbon into the embodied carbon discussion of a building. So number one, we just finished why this whole life carbon is a moving target, because it actually moves on the operational side and on the embodied side, depending on what is the life cycle you want to include, how many years, and also what type of building. They tend to be different. Second question, second topic. Why do we need to look at whole life carbon? Now, this is a frontier of operational carbon on the x-axis and embodied carbon on the y-axis, a paper done by European universities. If you just optimize operational carbon, you can have a really, really high embodied carbon building, really beef up the envelope, insulation, very strong envelope, a lot of embodied carbon, and minimize the operational carbon. Or you can have a building that has really low embodied carbon and optimize the embodied carbon, right? So you can't put in really little insulation, really little stuff on the envelope, and your operational carbon is going to be huge because energy loss is going to be huge. But you optimize embodied carbon. In this paper, what it finds, the optimal is somewhere in between, meaning if you just optimize operational carbon, it is not the optimal point on this whole spectrum. Or if you just optimize embodied carbon, it is not the optimal point either. Now, but the interesting thing about this point is it's actually closer to optimize of embodied carbon than operational carbon. What does that mean? That means it tends to favor a passive building with strong envelope. Now that is difficult to understand. So I give you an example here. We have an office building about 2,300 square meter floor plate. This is Energy Plus, very conventional building. We have three options here: 40% window wall ratio, 90% window wall ratio, or a ventilated double skin facade. Now, ventilated double skin facade is basically a triple pane window with ventilation going through it, right? So if you look at this three option, which one has the most embodied carbon? Of course, the one on the right, because it has 3 panes of window compared to anything on the left. It's only 2 panes of window. It's a double pane window. So no surprise there. Dotted line is the insulation that is not rock wool. Solid is rock wool, more sustainable. No matter what insulation you use, if you move towards the right, the one with triple pane, absolutely more embodied carbon. But you know what's interesting? Well, this is what's interesting. Now, no doubt the 40% window wall ratio is going to perform better, but what is more interesting is the double pane, typical insulating glass compared to the triple pane with ventilation through window. It has more embodied carbon on the exterior wall, but because of that, it shrinks the MEP embodied carbon and also the refrigerant it requires for that system. And as a result, the bar on the right and the bar in the middle, the embodied carbon of the building is roughly about the same. Now, if the embodied carbon is about the same, obviously the one on the right with the ventilated double skin facade, energy-wise is going to perform better. So the learning lesson here is if you have a more passive building, has a stronger envelope, oftentimes it pays off because it reduces the MEP system and it also reduces the operational energy. But the second point of this discussion is you really don't know the optimal point of a building until you study the whole life carbon of a building, both operational and embodied carbon integrate together, right? Not separate. Now, finally, we look at 4 elements that impact whole life carbon. Number 1 is high performance building. So now let's look at an example. This example is a 10,000 square meter all electric building. Upfront carbon is 400 kilograms CO2 equivalent per square meter. And then the first building we're going to look at is a building has an operational EUI of 125 kilowatt hour per square meter per year. And the grid emission is not 500, the world average is 370 grams CO2 equivalent per kilowatt hour. Okay, so it's slightly cleaner than the grid in Turkey. So what you're seeing on the screen, the dotted line is the upfront embodied carbon. In its life cycle of 20 years, you're going to have more. Well, in its life cycle of 60 years, you're going to have to MEP replacement, etc. So you're going to have more carbon, right? So that 6,000 is the embodied carbon. Now, here is the 125 kilowatt hour per square meter per year line of operational carbon. And then if you have a more efficient building, let's say 50% more efficient, the operational carbon is 62 kilowatt hour per square meter per year. That is the green line. So what's that mean? Well, this is what it means. If you add the embodied carbon and the operational carbon, the building that is 62 kilowatt hour per square meter per year, the operational carbon is about 70%. The building at 125 kilowatt hour per square meter per year, the operational carbon is at 82%. So when you look at these two charts, you say, oh, wow, the operational carbon is dominating the embodied carbon. Why should we worry about it? Good question, and we will see why. Let's look at another scenario now. What if your building, like many of the European new buildings and many of the American buildings too, is going to go net zero operational? Now in Europe, the net zero operational day is actually 2030, right? And if you look at the global timing, this is most of the countries around the world. By 2050, a lot of this country, they are committing to a net zero grid or net zero emission, meaning their grid will be pretty much renewable energy by 2050. Either way, either you're going to go a net zero building or your country's grid, electric grid, may get to all renewable by 2050. Either way, right? If your building is going to be net zero, let's say in this case, I have a net zero building by 2040, I'm sorry. Don't forget, in Europe, by 2030, all new buildings should be net zero operational. So this is about 10 years behind that already. So we draw a line there. By 2040, 18 years from now, I will be net zero operational energy. Well, guess what happened? If today you are at 370 grams CO2 equivalent per kilowatt hour, you're going to draw a linear line of reduction from 0.37 to 0.02 kilograms CO2 per kilowatt hour, right? As a result, it is not business as usual emission, that linear line that just keep going up. You just start bend the carbon curve. So this is what happened with your 125 kilowatt hour per square meter per year building and 63. When you bend the carbon curve, this is what happened when you have a net zero operational energy building by 2040, or if your electric grid is all cleaned up by 2040. The operational carbon for the 125 kilowatt hour per square meter per year building is only 47% operational carbon emission in his whole life cycle. And if you have a 63 kilowatt hour per square meter per year building, only 30% of the operational carbon in its entire life cycle. Embodied carbon dominates the discussion. That is why we need to start focus on optimization of whole life carbon, because many buildings we are planning in Europe, 2030, you will be seeing all new buildings are net zero operation. So if you look at business as usual, the red on the left, or 2040 net zero operation, the green on the right, you see the operational carbon, the orange color bar, start reducing rapidly. Okay, how about refrigerant? Well, refrigerant is what we call B1, is embodied carbon. Why is it embodied carbon? Because it comes with the building, and during the operation of the building, they leak. But that leakage is a replenish of the embodied carbon, which is not the energy it needs to run the building, or the EUI of the building. So EUI of a building is not the same as refrigerant leakage, which is an embodied carbon. Now, in fact, in this EN 15978, B1 is leakage of carbon, B6 is operational energy. So they are not the same bucket. One is embodied carbon, the other is operational. But if you look at scope 1, 2, 3 emission of an organization, not a building, then scope 1 emission refrigerant is under fugitive refrigerant, that's refrigerant leakage, is scope 1 direct emission of an organization. Those scope 1, 2, 3 is not the same as whole life carbon. We should be mindful of that. So this is the upfront carbon, is 10% more adding to the upfront carbon if you add refrigerant, and the whole life embodied carbon is 20% more. So again, if you draw a line at 2040, well, what happened after that? What happened to the GWP, global warming potential of refrigerant? What we are seeing is rapid decrease in the GWP in many of the chillers that coming out. So what will happen to refrigerant leakage in the future, right? So if we include refrigerant leakage in the business as usual, the linear projection with no net zero building is not very significant, 4 to 6%. But if we look at a net zero building, refrigerants start becoming more important, is 12 to 15%. And this is not even, this is not R410A, right? So this is still a R134A. So it's already a little bit better than R410A. So, and then if you look at the comparison again of red on the left is business as usual. The grid not going to get cleaner, nor your building is net zero. Versus the right, the building is going to be net zero, or the grid's going to get cleaner by the year 2040. The refrigerant impact is the gray bar. So finally, what about discount rate of carbon? Well, why do we need discount rate of carbon? Now, the US government discount carbon with a social cost, that is a dollar sign assigned to carbon because of the impact to the economy in terms of financial and dollar. It's about 3 to 7% more carbon in the atmosphere. It increased the cost by 3 to 7%. So Chemium and other software estimate the time value of carbon is about 3%. Potentially, it is the carbon inside the atmosphere. If I emit a carbon today into the atmosphere, right, it stay in the atmosphere that much longer than a carbon I emit 10 years from now. So that's why there's a time value of carbon. Let's use 3% example. By the way, this is not well understood and not well established, right? So this is a little bit of a guessing game here. Let's use 3% time value of carbon. What happened is the chart will become like this. And then if you go back to the bar charts, the time value of carbon on the right is the green, is the net zero future, right, with the discount. On the left is the net zero future with no discount. The impact is not significant, right? Because that has already ended in 2040. So your discount of carbon is only going up to 2040. It's not very impactful. But if you look at whole life carbon of 60 years on the red, is business as usual with no discount. On the right is business as usual with discount. Now, because your operational carbon lasts for 60 years, so if you discount anything by 3%, it has much more impact, the green box on the right, compare to you do not discount your carbon, that is the red box on the left. So as you can see here, even 3%, it has a huge impact to the carbon impact if you start discounting them. So with that, it's going to draw to a conclusion. I just want to summarize with you that today we talk about 3 things. Number 1, why whole life carbon, no matter it's operational or embodied carbon, is a moving target, right? It's not easy to establish all the numbers yet. Number 2, when you optimize carbon, you cannot just optimize operational ore and body alone. You have to look at that together, not in silo, in order to get the true optimal. And number 3, the 4 elements in whole life carbon and how they impact the whole life carbon. With that, this is the end of my presentation. Thank you very much.
Okay, thank you, Luke. It's really a great brief explanation of the decarbonization. It's really widened our perspective, actually. Thank you so much. Well, actually, as I told you, that if you have questions to our speaker, you will just use the questions part on the panel. But I just see just one question, but also I see one hand here, if I'm not wrong, from the audiences. Let me check if I'm not wrong. Sorry for making you wait. No. Okay. So maybe it is better to make a discussion at the end of all the presentations. So there is only one short question to you, Luke. I just want to, maybe you would like to make an explanation of, because one of our audiences asked that why R124A is better than R410A. So this is related with refrigerant, I think. Yeah, okay.
Yeah, so here's why, because it's the global warming potential. Global warming potential of 1 is equal to 1 unit of carbon dioxide. 134A is about 1,430 global warming potential, GWP. R410A is about 2,088 global warming potential. Right, almost, not quite, but almost double the amount of 134A. By the way, if you are in US, R410A, you're not allowed to use that in 2 years because of the GWP. In fact, in US right now, there are 4 states you have to use GWP of 650 or below. Okay, and then if you work with certain organizations, for example, if you work with Google, they have a requirement on the GWP, not more than, I think it's 150 or 125, roughly about that range. So that is why it becomes tricky. I mean, think about if you're building a base building for Google, right? You cannot use 134A. You have to use something below 125, but that's the world we are seeing right now.
Okay, I think this explanation is enough. Well, actually, one of our audiences, which is our professor and previous president of TTMD, Professor Birol Kılkış, would like to ask a question, but maybe he may extend his question. So may I ask to the technical team, is it possible to give a open the microphone of Birol Hoca? If it is not, I will ask here his question.
Yes, now Mr. Kılkış can ask his question.
Okay, Professor Kılkış, nice to have you here. Will you please ask your question? I think your microphone is on. Hocam?
I think now you can hear me.
Yes.
This is
Yes. Thanks, Hocam. Yes, we are listening you.
Thank you, Gülsu, and thank you, Luke, for very eye-opening and excellent presentation. My short question is, among your four elements, did you include also the second law of thermodynamics, which relates additional carbon dioxide emissions, not on site but elsewhere, due to exogenous destructions of the all electromechanical elements, thermal energy conversion systems, etc. Because otherwise this could be a fifth element in your calculations and predictions. Thank you.
Thank you, Hocam.
Can you
Yes.
repeat the question one more time? Sorry, that is cutting in and out a little bit.
Regarding your 4 elements, my question is, does one of these or some of the elements include the carbon dioxide emission responsibilities due to exergy distractions in all electromechanical systems and energy conversion systems in the built environment? Otherwise, we need to add a 5th element into the predictions and calculations.
Exergy.
Oh, exergy. Okay.
Mhm.
Wow, that is really good question. The answer to that is what I did was I basically use whatever is available in the industry to do those calculations. And I'm not 100% sure it include all the exergies. And I will imagine they might have missed some of them, but I'm not 100% sure. But this is a great topic that I think we should think about a little bit more. I'm not 100% sure whether that include all the exogen. Chances are they might have missed something. That's just my suspicions. So yeah.
Well, thank you. Actually, you are right. But to my own observations, the industry and all academia even include only the first law, energy efficiency, energy conservation, renewables, but not the exogenous distractions which take place due to the mismatches between the supply and the demand quality of the fuel, including renewables and the demand. And directly, the exogenous distractions relate to additional carbon dioxide emissions, not on site. You cannot measure it on the chimney, but it is a responsibility because someone, somewhere, sometime has to offset these distractions by using more energy. So this is a complicated.
Yeah. You know what? On that note, a typical EBT has 7 dimensions. It impacts the land, the air, and water. All the carbon calculation is just impact on the air, and also not including everything, just the carbon dimension. For example, right, the EPD has a dimension of impact on water called as eutrophication. That is the amount of nutrient, nitrogen, and phosphate when we create a material. It actually have some impact to the water potentially, increase the amount of eutrophication because of the nitrogen runoff. That sort of exergy is not included into this equation, and as a result, it could impact additional carbon emission in our environment. So in that regard, the EPDs and the carbon calculation we are doing right now does ignore a lot of the other 6 dimensions of the EPD, which impacts the land, the water, and even the air. We didn't include some of that ozone creation due to the material we use in embodied carbon. So, there's a new index coming up in Europe. They collapse all these dimensions into one number. But I think that will be the next time discussion, and we can talk about how to apply that number.
Yes, I am looking forward for next discussions. I am very pleased to meet you, and thank you very much for your beautiful and excellent presentation. Thank you so much. You are very helpful.
Okay.
Thank you.
Thank you for your insightful question, Professor.
Yeah.
Thank you.
Okay, Birol Hocam, thank you so much to you as well.
Thank you so much.
You know we have a time shortage, so if you have further questions, please just write on the question panel. But now, Luke, thank you so much again for your nice and very fruitful presentation. Now, I think it's time to go to the second speaker, today's second presenter, who is Dr. Drew Crawley. Today is going to give us a presentation on the impacts of climate change and urbanization on future building performance. Before I leave the screen to Drew, I just want to introduce him to you shortly. Drew Crawley is Bentley Fellow and Director, Building Performance Research focusing on building performance, zero energy buildings, decarbonization, digital twins, smart cities, and sustainability. Before elevation to Bentley Fellow in 2014, he led development of Bentley's building performance software for 4 years. Prior to joining Bentley, Dr. Crowley developed and managed Energy Plus and the US DOE's Commercial Buildings Initiative, promoting net zero energy buildings. With more than 40 years of experience in the building energy efficiency, renewable energy, and sustainability, he has worked in engineering software development, government research, and standards development organizations, as well as building design and consulting companies. He received his PhD in mechanical engineering from the University of Strathclyde in Glasgow, Scotland, on the topic of building simulation as a policy tool, and a Bachelor of Architecture from University of Tennessee. Mr. Crowley is active in ASHRAE, Director at large on ASHRAE board, member of Task Force on Building Decarbonization, and member of multiple standards and technical committees. He was elevated as ASHRAE Fellow in 2009 and received the ASHRAE Exceptional Service Award in 2013. He is also active in International Building Performance Simulation Association, IBIPSA President since 2022, Fellow in 2012, and Past President of IBIPSA USA. He has written more than 150 papers and articles, testified before the US Congress, lectured in more than 45 universities, and made more than 500 presentations on building energy efficiency, sustainability, and decarbonization through the world. As you see that, I got tired to introduce Drew. Thank you, Drew, being here together with us today. Now the screen is yours.
Thank you, Gülsu. And I want to thank the ASHRAE Turkish Chapter and TTMD for the invitation. Always love to be able to talk there. I had the pleasure of being in Istanbul last October when the ASHRAE board was there, and to meet many of the local people. So my presentation is a bit long, so I'm going to move pretty quickly here just to give you an overview. But so my talk's on climate change and urbanization impact on future building performance. I will tell you that if you can't quite get to the end, the impact on future buildings is actually quite small, particularly if we do a good job of our buildings. So start off with weather and climate are not the same. The terms are often used interchangeably, but weather is what's happening now. It's the temperature, moisture, wind, cloud cover, atmospheric pressure. It's what gets reported on your mobile phone app or on the television or the web. Climate, on the other hand, is a composite of that over many years. In meteorological terms, meteorologists use a term they call normals, and normals are a 30-year snapshot. So the normals we're using now were 1991 to 2020. So that's what when they talk about it's above normal, that's what they're talking about. But it is that range of climate that's happened in the past, not what's going to happen in the future. Weather is quite variable. This is a 12-hour snapshot from National Renewable Energy Lab in the United States near Denver, Colorado. The green line you see there is actually the solar radiation, the direct solar on that surface, and you're seeing it change. This is a 1-minute data set, and most of the data that we look at are hourly. So you see it changes quite regular throughout the time. You see it drop off about 1400 in the afternoon. In that particular area of the US, in summer afternoons, it clouds up. It doesn't necessarily rain, but it does get cloudy. So that's why we're seeing the solar radiation drop off. Excuse me. The New York Times has been doing a really great series of articles. This one, 2016, of course, was a global hottest year. Wasn't so much so in Istanbul, although it was 3 degrees Celsius above normal in Istanbul. And you can see that the gray area is kind of like the normal range, the range that you would see, and almost the entire year is above that in most months, at least. When I show this chart for other cities, what we'll see is in the spring and the fall times of the year that we'll actually see all-time high temperatures being set for that. So it is does vary quite a bit in what you see for very reason. I did a presentation for Brazil yesterday, and they're having the same issue, except that March and April of 2016 were actually quite cool years for them. So they were below normal for that year, so it's not evenly distributed. Similarly, 2019, a second hottest year. Again, we see much of the year is above the normal range throughout the year, not just the summer months. And you will, when you see this, you'll see that much of the change is not so much in the summertime, but in the spring months, spring and fall months, and sometimes in the winter as well. Climate change, looking at data, and this kind of shows you a impact starting in about 1850, looking at the globe. Gray areas are where there were no data available, but you'll see at the bottom the global mean temperature compared to recent data, and seeing the range varying about 0.5 degree down. Most of the 19th century beginning to move up a bit into the 20th century. But you see that it's not evenly distributed every year. That we get data where it's cold years in Europe or very hot years in Asia or at the North Pole and so on. So by the time we moved into the 1970s, now we're beginning to see more and more red. And by the 80s and 90s, you're seeing that increasing. So globally, we're getting almost entirely red, meaning above average. And you see that on the bar chart as well. And then we get to the hottest years here. You see 2015 hot globally, a cold spot there south of Greenland, probably due to ice melting. But then 2016, you see it was very hot globally, and then moving on. So 2019 was a particularly hot year as well, particularly in the south. In Africa and South America, there were hot spots. Australia particularly hit hard that year, and that was one of the leading causes, adding to the wildfire wildfires they had that year. Global average temperature, this is a global average, and this is when they talk about temperature change, this is what they're looking at. By 2021, we're already looking at 1.2 degrees from that historic period, and that's a big change that you are already seeing. We're not talking about 2100, we're talking about today. 2020, particularly hot in Siberia and parts of Asia. Europe was quite hot in 2021. North America had a hot spot as well, and then this past June as well. But one of the interesting things, this came up in my paper this morning, Greenland on Monday was 25 degrees above normal, 25 degrees Celsius above normal. And the normal jet stream was driving a lot of the hotter weather that's been on the eastern and central US up over the ice in Greenland, causing a huge meltdown going on there right now. And that variation, that change is what we've been seeing recently. If we look at Istanbul specifically, there's a great website, Berkeley Earth, that has data. You can go in and enter any location and look at the long-term trends. And what we're seeing here, for example, is over the last 25 years, we're seeing temperatures in Istanbul that are up about 1.5 degrees for that time frame. That's average over the year. But the other thing they show is which are the months contributing, which are the hottest and coldest. The yellow ones are in the past 20 years, the hottest sector. And you see there are only 3 months that even show up in the top 10 for the coldest months for that period. However, if you look at the hottest months, it's almost all in the last recent years. Yes, there are some that are older, but for the most part, they are recent months. A great book if you're interested in building performance simulation, which has been sort of my career, and there's a section on weather and climate related to that. This book has good information about the basics of simulation and details about specific systems and technologies that need to be dealt with, all the way up to urban scale physics and simulation for that. But I'm going to use it just to talk about some of the climatic data we need. If we're doing a full simulation, I'm not going to detail all this, but if we're doing a full simulation, we need typical full year data, and hourly is about the best we can normally do. If we're doing equipment sizing, we need design day information, such as that we can get from the ASHRAE handbook, and other variations there. So it's not all the same types that we need. But one of the issues we have is that there's not good data for a lot of the weather data universally throughout the globe. Dry bulb is pretty commonly observed. We have good data there, primarily from weather stations at airports. Humidity, similar. Solar radiation, there's almost no data measured globally on a regular basis. Solar luminance, the same. Wind is also a bit problematic just because the local effects of, is it open terrain, is it hilly, is it urban, etc., will change a lot of that as well. So some of the data are just not there. But one of the nice things about climatic data is that in the past it's only been available from these ground observation stations, these airport stations. Temperature, humidity, robust, wind, problematic, and it rarely includes solar data. Rarely, almost never includes solar data. And then we may have some limitations on other data as well. But now with 20 to 40 years of satellite data, we're now beginning to see very good quality of that data. NASA has been working with the ASHRAE Technical Committee on Climate Information to look at the information and see whether it's possible from the remote sensing, the satellite data, to actually replicate the ASHRAE design conditions. They're actually quite good for that. The master data sets, there's one from the National Centers for Environmental Information. It's updated near real time. This is a repository of weather data globally that's stored for the World Meteorological Organization. But we can't use the raw data. We need some analysis and data filling before it can be used. The design conditions are generally based on a historical period of record, and that means we lag. So the handbook is not, even though it may be at 2021, it won't include data all the way up into 2021. Also limited solar radiation we mentioned before. So design conditions, as design engineers, you're probably very familiar with using those to size and select equipment for heating, ventilating, air conditioning, but they're also used in other sectors, residential, agricultural, commercial, and industrial applications as well, not just the HVAC industry. Usually it's dry bulb, wet bulb, dew point, and wind speed at various frequencies. And the concept used within the ASHRAE handbook is the idea of a percentile. That means that certain number of hours in a year, or percentile of hours in a year, you would expect temperatures to be higher or lower. So 99.6 means about 35 hours a year. It'll be colder than that, not too many hours. It won't be all the same day or one period. And the other typical is a 1% on the cooling dry bulb. This is for traditional design, nothing requiring closer control. 1% on the other hand means about 88 hours a year. So, but there are other percentiles. So there's a 99, a little less strict on the heating, also 0.4, 2, and 5 on the cooling as well. And since 2012, the Load Calculation Committee has recommended using monthly cooling percentiles. And the primary reason for that is with the sun angles so high in the summer and July, August timeframe, we're not actually getting much direct sunlight on the glazing. And we often will get peak conditions, peak cooling load conditions in September or October, I've even seen. So it's better to use the monthly cooling percentiles. Now the monthly percentiles, the 5% monthly is equivalent to about the 1% annual. So the handbook, the 2021, is the best source that has about 9,200 locations globally. It is based on that data from NCEI through 2019. So it doesn't include the last 2 years, but there's some processing time that it takes to generate a data set of this scale. But we have looked at the climate conditions that have been changing. There was a study for the 2009 handbook that looked at that the 99.6, that heating dry bulb temperature was increasing about 1.5 degrees globally, and the 0.4 about 0.8 degrees. It varies all over the place. A more recent study, this was for the 2017 handbook, showed that it varied from 0.2 to minus 0.2 to plus 0.2 variation, but there was a slight signal overall that showed a change of about 0.05 degrees a year. So about 1 degree every 20 years is what has been seen already. So the handbook has quite good data for the Northern Hemisphere and a bit less good in the Southern Hemisphere, particularly if you look at Africa. Until the 2021 handbook, there was no design condition for the largest economy in Africa, which is Nigeria, and still the fastest growing economy. There is one now, but that's still a problem. Africa is a bit sparse on there, but we have some new sources that can help with that. This is the ASHRAE web-based station finder. It allows you to look up data for that. You can click, say, I want a specific country, and click on Turkey, and then it'll show you all the locations related for Turkey. The numbers in there indicate how many stations there are within that locality. So Greater Istanbul, we have a number of stations right around the Marmara Sea, but the data, of course, is old enough that we don't have the new Istanbul airport, but the Ataturk data is still there, and we can take a look at that. The standard output is this one pager, but that tool allows you to do all sorts of manipulation of the data and looking at joint frequencies and other things that I'm not going to cover here. But a one page kind of summarizing annual conditions, monthly conditions, etc., all in one page. So let's look at it in a little more detail. The top part is the annual heating. So there we'll see the heating dry bulb 99.6 for Istanbul is about minus 1.4. There, the annual cooling, the 1% dry bulb 30.9, and the hottest month is August. And you have other evaporation, dehumidification, enthalpy variations on the cooling side. Then the next section in these stream annual conditions, they have a set of statistical based information saying that statistically based on the information of the past, the return period, as they call it, is for 50 years, it could be up to 39 in Istanbul. So the next section is monthly design conditions. So we have temperatures, degree days, degree hours, wind, precipitation, the monthly percentiles for dry bulb, the monthly percentiles for wet bulb, and a mean daily temperature range. So you have them biannual and also by month for these data. At the bottom, the last three sections, the daily temperature range varying by month, and also the clear sky solar irradiance for that. And that's for the ASHRAE design calculation conditions. Clear sky and all sky solar radiation variation with the variables you need for doing that. The last section, the historical trends, is what's new. And there is it looks at the long-term data set for that location, but also its neighbors. And in this case, the average dry bulb over the last 30 years has seen about a 0.75 increase. The cooling 1% about 0.6, and we're seeing some drops in the heating degree days and increases in cooling degree days. Not all locations have this sort of signal. This is one of the stronger ones I've seen. I mentioned the NASA project. This is NASA Power, and they can replicate the data and that you can get here so that you can, for any point on the planet on a 5-degree grid, you can match the design conditions within about a half a degree Celsius, and that is a useful thing to do. It has data for only 2001 to present, but that's where a lot of the data are now. So it's been out for about 1.5 years. It continues to get more robust. They're going to take the grid to a smaller grid over the next year or two. Building simulation, I mentioned earlier. We need to have climatic data so that we can simulate performance from a single year analysis. There's a methodology, typical meteorological year. It's most widely used. Essentially, is a composite of months. It might have January from 2015. It might have February from 2011, and the whole year put together as a composite. But each of them is representative for the period record. There's an ISO standard which also uses that. The months are selected based on statistical indices, daily, min, mean, and max of multiple variables. But the weights of those can change depending on the methodology. The ISO standard doesn't recommend a particular set of weightings, but the TMY has kind of an equal weighting basis, and but I've seen others that overweight solar radiation if you're more interested in that. Some of the data sets available, the TMY data sets, though, are best for comparing alternatives. They're not intended to tell you what the energy use of your building is going to be. It is a kind of a comparative number. Compliance with building standards and codes which use performance methods, and getting points for green building rating systems. But there's no effort in there. In fact, the effort is to get typical, not extreme conditions, and they don't necessarily cover or represent the design conditions. There are a lot of typical data sets available. There's including one from, and I'm not seeing it on here right away, but there is a data set for Turkey as well. But there's a new data set there at the bottom, typical meteorological year, which includes data for 16,000 locations up through 2021. In the US, we're using quite an old data set, TMY3, which came from one of the national laboratories, but the data are very out of date. It only includes data through 2005, so there's a limitation on that. But this is just a subset, really, of the data sets that are available out there, and you'll see more and more as they come through. Actual weather data, if we're trying to retrofit an existing building and we need to calibrate its energy use to utility bills, we will we'll see that we need maybe a couple years, maybe 3 years of actual weather data. There are many sources. I mentioned the National Centers for Environmental Information, NCEI. That data is free, but then Weather Bank, Weather Source, Weather Underground are all private organizations who sell and package weather data. And also the National Meteorological Office will often make data available. The same data that the National Meteorological Offices use is provided back to NCEI, but they don't necessarily have all the stations that the country offices are collecting. But how complete are they, and does it include what we need for energy simulation, temperature, humidity, wind, solar radiation? This is an example of using typical weather. This is the location. This is actually just 10 kilometers from my house, Washington, D.C.'s National Airport. And it's the completest data set I've seen. I've seen data sets in Europe, that hourly data sets that date back into the early 1930s, but this one starts in 1937, but it's complete from 1938 to present. What I've done is simulated a small office building showing the change. This only has data through 2016, but for this chart. But the oops, sorry, went the wrong way. The typical TMY for this location is there on the right side. And if we drew a line, as I just did, you'll see that it does what it's supposed to do. It's not the most extreme, most energy, and it's not the least energy. It's kind of in the middle, not a mean specifically, but close to the middle. So what's happening? Past 5 years have been the warmest on record, and our design conditions are only updated by ASHRAE and the fundamentals every 4 years. So, the 2017 came out, and already 2016 had been the global hottest year, but we didn't reflect that. As I mentioned, like the TMY3, the TMYs are not updated very frequently, so that means they can lag as well. So does it matter? And we did a quick look at a few locations. There's the older US data sets, but also some of the international weather data sets, and this newer TMYX data set that I talked about had data through 2021. Looking at the TMY type data, this is how the heating degree days have changed. And you can see there's Buenos Aires, Cairo, Denver, London, Los Angeles, Madrid, New Delhi, Sao Paulo, Singapore, Washington Dulles near me, Winnipeg up in Canada, and the highest one there, Resolute, above the Arctic Circle. And you see in almost all cases, heating degree days have changed. The exception there is Singapore, where it doesn't ever get cold enough to have any heating degree days. Cooling degree days, of course, we'd expect to see the opposite trend, and we do. See, Cairo, for example, is increasing about 10 to 15% over that period. And Delhi on the order of about 10%. Singapore, same sort of change. So we are seeing the change over that period. Washington Dulles about the same scale, maybe even 15% there. So you can see how different locations are changing. So, but how does that mean the design conditions are changing? And what we have here, the locations listed alphabetically. The lightest bar is the 1997 handbook, and the darkest red bar is the current handbook. And what you're seeing is that design conditions are increasing. So if I went to Cairo, for example, the winter design condition went from about 8 to 9.5. And other places, Singapore went from about 23 to 24 as the heating design condition for that. Sao Paulo from about 10 to 11. Delhi went down slightly for the heating side. Madrid from about -4 to -3. So you do see a trend for the most part to warmer design conditions for heating. If you go the other direction and look at the cooling side, the cooling design conditions, we see almost uniformly all of the conditions are increasing. And you often see that last increase is actually quite a little bit of jump, almost a half a degree in many locations. That's because we're connecting with that data up through 2019, which includes the 2 warmest years globally, and we're seeing that change. The one exception is there at the bottom, and that's Winnipeg. And I don't know why Winnipeg's getting a little cooler in the summer, but it is there. This shows simulating the same thing. Now we've seen the design conditions shift a little bit, but it's interesting that you're not seeing the increase in energy use you would expect. And part of that is if you look at the red portion of the bars the stacked bars, what you're seeing is that decreasing. Let's look at Washington Dulles there, second from the right, and you see actual overall energy use is decreasing. What's happening there is that heating is decreasing more than cooling is increasing. This is a site energy use, not a primary energy use. If it were primary source energy, it would likely be a little more of an increase. So heating's decreasing more than cooling's increasing is what's happening. So we're seeing almost no impact here, a little bit more. Los Angeles, New Delhi, Singapore, all of course being hot climates, so looking at what's going on there is important. If we just look at the heating and cooling, you can see the trend a bit more direct. Looking at New Delhi there in the middle, of course, cooling increasing across the three variations with almost no heating to begin with. The same for Singapore, though a little variation there. So definitely we are seeing that trend. The other thing that happens is there's heat island effect. There are 3 of those weather stations on this map. The far left, that's Washington Dulles Airport, which I've been talking about. In the center, just below the word Washington, that's actually the District of Columbia, that portion of the square there. That's Washington National Airport, which had the long-term record. And then there's another joint Air Force base there off to the right. In 2018, NOAA came in and did a look at the heat island for the particular location, and they measured it all over the city. And what you see there is a variation of about 10 to 12 degrees between hot and cold. We see cooler temperatures prevailing up the river. That's the river that flows through Washington, the Potomac. But then we see much hotter in kind of the central area where all the businesses are, and the White House and the Capitol, etc. But you see there's kind of a blue piece right there next to that. That's actually a national park within the city, and that has old growth trees in it, so it tends to be a lot cooler. The difference between that and the center, the city center, are on the order of about 10 degrees. Now this is at a particular time of day, not average, but definitely seeing a trend there. So for creating future climate, there are 4 major methods for doing this. The first 2 involve very computer intensive methods. Dynamic downscaling takes these global simulation models and downscales them to a smaller grid to be able to use that more locally. Statistical models try to look at the all the data related to distributions of weather variable and how they interact. So it gives you not a single path forward or a single view of where the weather will be, but where there are different scenarios of where it could be. And so any of the outputs from that can be possible, both very computer intensive. The one used most is time series adjustment or morphing, and I'll talk a little bit about, show you an example of that. The easiest one is the analog. You just try to find existing locations that already have data that are comparable to what the predicted climate change scenario is showing. So I don't have one for Turkey specifically, but this is an example of that for the US, showing how temperatures are moving from cooler to warmer, more humid conditions for that. This is an example. This was for Grand Rapids, Michigan, up kind of northeast of Chicago, and it's going to get a lot warmer and more humid, more like Philadelphia is today. So quite a bit of change there, saying 2.8 degrees warmer and 20% wetter. Now, I'll talk about what that might mean in Istanbul later, but I want to go through the rest of this pretty quickly. The IPCC, the Intergovernmental Panel on Climate Change, has a set of scenarios, and these are just storylines to represent the range of what could happen in social, economic, technological, and environmental issues. They are updated for each assessment report, which are done somewhat irregularly. The last data, the assessment report 5 was released 2013, but we're beginning to see data for AR6. It just hasn't been out there yet. The scenarios, they are called representative concentration pathways in the AR5, and they're derived from the storylines. What's going to happen? What's going to be the cause or the result of the different storylines in terms of their climate impact? You see here they vary quite a bit. The RCP 2.6 is if we do everything we possibly can, if we do control climate change to 1.5 or maybe 1 degree C. Very difficult to do. I don't think we're going to get there. The 8.5 on the other hand is showing a global average surface temperature of up to 4 degrees, but you see there's a range, almost 6 and down to 3 for that, and similarly for the RCP 2.6. So these are basically different runs by different models of the global circulation that are used within this group to calculate the change. So to morph a data set, we start with a base data. I'm going to use TMY data here. It has an average monthly temperature change, usually an increase. There's a change in the diurnal range of temperature, daily range, sometimes plus, but usually more likely a decrease in that. Some cloud cover change, which changes solar radiation, and then precipitation. So this is an autumn day, a fall day in Los Angeles, November 23rd, quite nice day. It starts off at about 12, gets up to about 21 during the day, and that's the yellow line. The other 4 lines represent what the data are when they're morphed. There's a base daily range or diurnal temperature. There's a scenario diurnal temperature, often a little bit fewer degrees, so the night times tend to be warmer. And then we have a temperature delta for that to calculate the difference. So it's not just simply adding a temperature, a delta temperature, it's also looking at how it changes throughout the day. Heat island can be represented similarly. This is based on several measurement studies I've seen done before the 2018 study for Washington. The annual average range is roughly 1 to 5, and it tends to be seems to be a function of city population. Beyond 5 million, it kind of stabilizes around 5 degrees C. It tends to depress the daytime temperature. All the hard surfaces, the mass is absorbing heat all day long, but it also, after the sun sets, it tends to raise the nighttime temperature. So this is what one looks like. Here's Washington Dulles, a spring day, April 10th. Can start off cold, like today it started off at 4, and in this case it's moving up to about 17 during the afternoon. That's the yellow. And then you see the 1 degree, which is the red, and the blue is the 5 degree range, and seeing what's going on there. We've got lower daytime temperatures, not a lot, just half a degree or less, but the temperatures tend to remain higher. As that mass begins to give off its heat, as the air temperature drops, and the solar radiation goes away, it tends to keep the air temperature higher. And they stay higher till about sunrise when they go back up again. But you also see that diurnal variation is a lot less under this case. So here's an example of what that means. This is Dulles again. We have the TMY data there, and then we have the 4 RCPs or scenarios for that. And your monthly data showing the variation. Pay attention to the red and the blue, though. Those are the key things. So in Washington, we don't really start getting cooling until March, and it's not a lot of it, and it kind of extends into October. But our main heating months are November to March. But then if you look at some of the scenarios, particularly the far right, you're seeing a little bit of cooling creeping into those months, and the cooling itself is going up significantly in the summer, and it's spreading toward those shoulder months as well. So that's not unusual for what you see. This is kind of a mixed heating cooling climate. So let's look at some of the others. This is a snapshot looking at Washington Dulles again, but site energy, it means overall that it's about the same. If we look at source or primary, we are starting to get increases, but that's due to the cooling increases outweighing the heating increases in this case. But if we take that building and design it to be 50% of code, a low energy building, we can mitigate those impacts almost entirely. It reduces that variation there entirely. If we look at Singapore, Singapore doesn't have heating and cooling to trade off. So we're seeing increases on the order of 20% or so in cooling, sometimes 30% for the various scenarios. It's just going to get hotter. Low energy buildings, though, can have the same effect in Singapore as they do elsewhere. They can mitigate most of that impact for us, which is great. The other extreme, this is that Canadian location in the far north, Resolute, and you see that heating's dropping on the order of about 40% due to the scenarios for that. Low energy buildings also, but mostly they build low energy buildings there anyway. They have to be very efficient. It's a location that it rarely gets above 4 or 5 degrees in the summer. So very much a heating dominated climate. Here's a look at Cairo. Cairo, you're seeing definite increase in the cooling on the order of about 25%, looking across the various scenarios. But you see there is a little bit of heating there where it does get cooler in November through February timeframe. Not quite like Washington, but definitely a change. But if you look at it from a primary or source energy viewpoint, now we're seeing 30 to 40% increases in just the cooling aspect of it, overall in the range of 15 to 20%. Now that's a significant change for that particular location. If we look at it on a monthly basis, you see the little bit of heating out January, February, October, November, November, December. But now look at how much more cooling is going on in the summers. And that's partly that the nighttime temperatures are going to be remaining higher in these locations. Is not necessarily the peak temperature that's driving this. If we look at Delhi, similar sort of thing where we'd have some cooler months, January, February, November, December, and the summer months and the cooler months are all seeing significant increases. We're looking at a tripling of cooling in January, February timeframe for that location. So just a lot more hours of operation for that location. The largest change overall.
Sorry, you have a few more minutes. So if you just shorten.
It's my next to last slide.
Okay, good.
So this is the monthly energy end use that we've seen before, and you see how that's changing. Sao Paulo, the top right, I haven't shown you, but you see that there's a little bit of heating demand. They don't really heat very much in Sao Paulo, but extending over into the other scenarios, that almost disappears, and substantially more cooling throughout. So with that, I'll go to a summary. We have to have climatic data for doing our building design, our HVAC systems sizing and selection. We need building simulation. We need typical, actual, and future data. There's been some work on trying to bracket that typical with extreme meteorological years. No real conclusion there yet, but we have sources of data now that were unavailable even a decade ago, both the traditional airport ground observing stations and the satellite data. We can represent the climate change scenarios in this data set by using morphing, modifying files. Higher latitude climates are going to see decreases because heating's decreasing more than cooling, but tropical, semi-tropical are likely to see increases, but primarily due to increased cooling. But the good news is that we can mitigate most of that impact by going with zero energy or even 50% lower than code requirements that can mitigate most of that impact and make our buildings kind of resilient and climate proof. But overall, significantly more hours of cooling equipment operation. And that's something I'm looking into right now. So what can you do? Design the best building you can. If you're concerned about potential impacts, look at the next warmest climate. Is Istanbul, Cairo, Istanbul to Beirut? I'm not quite sure how the climates compare. I know Istanbul is quite affected by the water there, so it's not clear. Maybe it's Alexandria. That might be a better view there. But Delhi to Mumbai, Boston, New York City, and look at the design conditions and see how different they are. And if you're doing simulation, you could use one of the a climate file from one of those other locations and look at the impact. Last, I'll just say that data set, 16,000 locations, there's quite good representation, I believe, over 100 locations in Turkey at this point, and data are available there. So that, I'll leave it and say thank you.
Okay, thank you, Drew. Thank you so much. Actually, this is really nice to hear that. As far as we know that this climatic issue is the most critical point of our future design, just developing our future design principles. So this is good to hear that it is somehow possible to just mitigate the impact of the climate change by the precautions regarding to the zero energy or energy efficient strategies. But on the other hand, it's not possible to stop, I think, these climate change issues, so we need to adapt our future buildings based on the on these inevitable changes. If you agree with me, I don't know.
I agree very much, and I'm sort of sorry that Luke's presentation and mine weren't the other way, because this doesn't mean that we shouldn't be doing the best we could do and taking our buildings to zero. From the operational side, we have a lot to do, and they are a huge impact. 34% of global emissions are related to buildings. So if we're not doing something in our buildings, we're adding to the problem.
Yep, you're right. So I'm just checking if any questions here on the questions panel. If you have questions, it's not from now on possible to just give the microphone to you, but if you have questions, please write down to the questions part. If any questions, I'm just checking also on the chat part. Maybe Drew, you can see that Birol Hoca also sent his best regards to you.
I see Birol's report. Yeah, that's right. I do need to update.
Okay, so I think there is no any other questions seem. One or two audiences would like to get the PowerPoints later after this webinar. I don't know if it's possible. It's a technical issue. I just ask to you also first, the presenters, if they allow us to share, then I think it's possible. We will inform you later. One other audiences is still Abu Dhabi the highest wet bulb temperature in the earth, is asking. Do you know anything about Abu Dhabi?
Abu Dhabi, yeah, I actually did a presentation for Bahrain and Kuwait last week, and it's going to be extremely, maybe uninhabitable. There is just, the temperatures are 50, 55 degrees are possible, which is obscenely hot, and that does seem to be happening, particularly in those locations where it's drier. We're going to see the more extreme temperatures and the higher range of temperature.
I see. Okay, if any questions to Drew or Luke, I don't know. as I told you that it's maybe just write your questions here if possible. If not, Mr. Gökşin, do you want to say a few words to our presenters?
Thank you very much for both lecturers. It was very useful for me. I get a lot of information. I hope all the attendees get a lot of information. It was very important to know embodied carbon and decarbonization is getting more and more important, and we should be consider embodied carbon in our buildings then. And Drew explained the climate changing, how affecting the design. So it was very useful. Thank you very much for both lecturers, and thank you very much for the attendees also.
Thank you.
Yes,
Thank you
okay. I also would like to thank both of our speakers, presenters, for their nice presentations. And now I think it's time to close today's webinar. I also thank all the attendees and hope to see you somewhere face to face soon. So yes, this is the end, and I say bye-bye to all of you. Have a nice day.
Thank you. Bye-bye. Bye-bye.
Thank you. Bye-bye. Take care.
Bye.